Hey everybody, Mr. Bowman here. This video is on 3.14 probability distributions. Our focus is on all the merit questions for the 2024 exam. If you're looking for more excellence questions from the past NZQA papers, check out the link in the description below, and I've kind of compiled them all in one place for your convenience. So let's get straight into question number 33. So question 33. So the theme of this paper, if you've done it, it was a bit weird. They've had belly button and innies and outies and belly button fluff. It's a bit weird, but basically we're looking at someone's belly button can be described as an innie or an outie. They've even put a picture in the exam, but I didn't put that in here. So it's cosmetic, it's not a health indicator is what it's saying. Data on belly button type, and the world's first belly button survey was completed. It found that 96% of respondents had an innie belly button. So that information will be useful. So the actual question itself, so belly button fluff accumulates, so belly button fluff is the accumulation of fibers, lint and debris. It's found that 66% of respondents had fluff in their belly button. Using an appropriate distribution, calculate an estimate for the probability of 1 in 30, so one student in a class of 30 that had an outie belly button and contained some belly button fluff. You should state your probability distribution, the parameters as part of your question. So usual deal, always state your distribution, always state your parameters. So took me a while to think about this one here. So I suppose the first thing to think about was the way we're going to approach it. So to find this probability, we're probably going to need the probability that there was one outie in the class. And then we're going to need to multiply that by the probability that a random person would have had fluff in their belly button. And I want to note, because we're multiplying these two probabilities together, we are assuming some independence as part of this question. Forgive my messy handwriting. So we're assuming independence. So this probability of fluff is actually given to us in the question of 66%. So we don't need to calculate that, but we do need to do a separate calculation for the probability that there's one person in the class out of 30 with the belly button fluff. So let's do that first. So I guess the first thing to note is what distribution it is, and I'm leaning towards a binomial distribution because if you think of the context, there's only two outcomes, right? You either have belly button fluff or you don't, and that for me precludes all the other ones. So let's state down the distribution. So I'm going to use a binomial distribution. And I'm trying to find out the probability of exactly one. So I'm going to be using the binomial point distribution mode on my calculator. So for this calculation, we know that x is going to be equal to 1. We know n is going to be equal to 30. That's the number of people in the class. And the probability of someone having belly, an outie is going to be 1 minus the 0.96, which was the innie number. So that's 0.04. So from all that, we can put that into our graphics calculator and find out that the probability of there being 1, what was that? So the probability that of there being exactly 1 was 0.3673. And that they had a 4dp rounding, didn't it? So let's state my 4dp rounding. Okay, so I've got that part here now. So the rest is actually going to be quite cruisy, isn't it? I now just need to multiply this number by my fluff number. So the probability that there was only one outie in the class. I'm just going to write it in words. Only one outie. And they had fluff. That's going to be equal to 0.3673 times by 0.66. And again, plug that into your calculator. And when I did that, I got 0.24243. I just realized I rounded to 5dp there. I normally don't round to 5dp, normally round to 4, but done it in this case. So that was I think one of the nicer excellence questions going around. And yeah, it was a good one, easy excellence mark to aim for. Now into question number 34, and question 34 was a I and II part. You need to get both to get that excellence mark. So let's start off with the II, or the I section of it. So we've got very little research is done on the size of belly buttons. It is hypothesized that the diameter of the belly button, distance across the widest point, could be modeled by a normal distribution with a mean of 2.05 and a standard deviation of 0.9. Estimate the probability that a randomly selected adult that has a diameter of at least this number, given they have a diameter between 1.5 and 2. And then once you've done that, part I asks you to comment on the suitability of the parameters that you've used. So we'll get to that last bit there. Let's focus on I first. Let's get all the maths and the numbers done. So from the wording of the question, it's pretty clear a normal distribution is going to be used, right? So we don't need to state that explicitly, but just a reminder, if it asks us to select a distribution, we then had to state the distribution used and the parameters that we were doing as well. So let's break down the question a little bit more. So the question says that the people we're interested in have a diameter between 1.5 and 2. And of that group, we only care about those who have a diameter of greater than 1.5. So this is actually a conditional question. So let's kind of write this down in probability notation so we know what it looks like. So we're trying to find the probability that someone's belly button has a diameter of greater than 1.75. And just a reminder, in this context, that's greater than 7.5 but less than 2. So we got to find that given they had a belly button diameter of between 1.5 and 2. So we're trying to find that probability there. And to find that, we need to find the probability that someone had a belly button of between 1.75 and 2. And that's going to be divided by the probability that someone had a belly button diameter between 1.5 and 2. So we need to do two normal distribution calculations, one at the top, one on the bottom, to then be able to calculate this probability. So let's start by doing the numerator first. So let's start by finding the probability that the diameter was between 1.75 and 2. And for that, remember, it's a normal distribution, so best practice is to sketch it out. So we've got our normal distribution curve. We had a mean from the question of 2.05. Our question told us the standard deviation is 0.9. And we were trying to find between 1.75 and 2. So we're trying to find the probability of that shaded area there. And normally for these inputs, for these questions, you want to state your calculator input. So for a calculator, we're using the NCD mode, don't forget. You would be using a lower, which in this case was 1.75. You'd then be needing an upper, which is 2. You'll then need to state your standard deviation, which is 0.9. And then finally, you need to state your mean, which was 2.05. And when you plug that into NCD mode, you'll get the probability. So the probability that X was between 1.75 and 2. I'm just looking at my book here because I've already done that there. So that came to 1.04, so 1.084, and that there had a 4dp rounding. So I've got my first answer there. I now need to find that denominator, so between 1.5 and 2. So we're going to do a similar process. So we're going to find the probability that X is greater than 1.5. So 1.5, X, and then 2. Our calculator inputs and our diagram process is going to be pretty similar to the first one. So we draw a normal distribution diagram. We had a standard deviation of 0.9. We had a mean down the middle there of 2 or 1.05, and we're trying to find between 1.5 and 2. So let's call that 2 over there. That's 1.5, and we're trying to find that diagram there. Also that shaded portion. So again, let's get our calculator inputs. So we need a lower. So we'll just do alpha lower this time. Our lower, 1.5. We needed a U for upper, which was 2. We needed the standard deviation given to us 0.9, and then we needed the mean of 2.05. Plugging that all, again, same thing as last time. Plug it into your calculator, your NCD mode. Between 1.5 and 2, when I did this earlier today, I got 0.2073. Again, I had a 4dp round. Okay, the very final step, I can put both of these two probabilities here. I can put them together to find the total probability that I'm trying to find out, my conditional one. So I'm not going to write out the full notation here because I'm probably going to run out of room. So I'm going to write probability is equal to, remember, hopefully you're writing down the full notation for that. That's going to be equal to, what? Oh, it's not 1. 0.1084. Don't forget, that's the probability of it being between 1.75 and 2. And that's going to be divided by the probability between 1.5 and 2, which is 0.2073. That was down here. And when I put that into my calculator, I get my overall answer, 0.5229, and again that had a rounding to 4dp. P. So pretty messy question here, but hopefully you can see how these conditional questions work. It's certainly something I've noticed of late that's coming up more. It's a bit of an unusual question, but it's coming up a bit more. So hopefully it's something you'll be able to get a bit more practice of. We're now onto the I part. I've left my actual answer for I over here, just so we can kind of refer to that if we need to. But the next question is, and this is to wrap up the excellence mark because you needed both I and II to get excellence. Comment on the suitability of using the parameters for modeling belly button width. So the main issue that normally comes up with normal distribution parameters, and I'll sketch the graph here. So there's my graph there. It's a poorly drawn one. But hopefully you can see. So our parameters in this case was 2.05, our standard deviation of 0.9. The only real limitation on the parameters is whether or not it hits that assumption of there being no upper or lower limit. And in our case, there is a natural upper and lower limit, right? That natural and upper lower limit is 0 because you can't have a belly button width less than 0. So basically, if this probability distribution here, if this portion over here less than 0, if that is a significant portion, so, if it's maybe like, 0.0001% or something like that, then we could probably disregard it. But if it's a percent more than that, then it's going to be an issue. It means those parameters don't accurately account for the limitation of this context being you can't have a belly button of less than 0. So let's do the math of that first, and then we can discuss that in a bit more detail. So let's say we're trying to find this probability. So our lower, alpha lower, remember it's a whole bunch of 9s, so we're going to do -6 9s. Our upper in this case is 0, our standard deviation is 0.9, and our mean 2.05. And when you put that into your calculator, it tells you the probability of having a belly button less than 0, which obviously is impossible, is actually 0.0114. And that's actually quite significant because if you put that into percentage, that's about 1.14% of belly buttons. Based on this distribution, this theoretical distribution, it's not even possible to get those values. I've got a text box. I'm going to type up the rest of my response, but I guess ultimately here I'm trying to comment on the suitability of the parameters used. So my end goal is to state something like suitable or not suitable. I need to clearly answer the question with this evidence that I've gathered here, this 1.14% of belly buttons not being possible. So let's start talking about this upper lower limit negative diameter stuff that I talked about. So I started my comment on it is not possible for belly buttons to have a negative diameter. A normal distribution requires no lower or upper limit, which is not present in our context, as approximately so now I'm going to talk about the numbers that are 1.14% of belly buttons would have a negative diameter under the normal distribution and its parameters. So I've stated my issues. I now need to clearly answer the question about the suitability. So this suggests a normal distribution might not be suitable for modeling adult belly button width. So this suggests that a normal distribution and its parameters may not be suitable for modeling adult belly button width. So that wraps up this question. So as I said, both of those would kind of combined would have got you the E mark in this exam. But quite a lot to this one, II and I. Certainly was a lot, and that calculation preceding that was quite challenging too. Okay, so we're now on to question number 35, and question number 35 I actually thought was a really nice and accessible excellence question for any skill level. So let's go break down the question for. So the previous question had some information about a triangular distribution. It told us we had a minimum, a maximum, and a mode. So if we drew that on the graph, we had a triangular distribution that kind of, those three dots there were the parameters we mentioned. If we kind of connect them there, and connect this one down here, that was what this triangular distribution we used suggested. And you can kind of see there's a big issue right here. This big blank gap here, that does not, so the triangular distribution we've got does not really reflect the data because of that huge void. So let's keep reading. So the question then says, suggest alternate parameters for a triangular distribution. Basically, this means these numbers up here, we need to change them so the triangular distribution basically better reflects that data. So for me, I didn't mind this, this first one up here. So that one there was actually quite nice. Maybe I disagree with the one. It was slightly, because that mode was that bar there, and that bar was actually between 0.8 and 1. So it's weird that we've got the very right hand side of the mode of that bar as our mode. Maybe the midpoint is going to be a bit better. And the next one is, we need to think, well, what line can we draw this way that better reflects the data? And you can kind of see that one, if we start maybe connect it to 4, and I'm just making this up, and I connect that dot there, you can kind of see this line here straight away reflects it a lot better. We can see there's a little bit of a gap under it, but that's maybe netted off by the few bars that are overwards. So potentially this 4 one will be a bit better. But what I might do is, knowing therefore, I might actually take it to 4.2. So that kind of includes that one bit of data before the gaps and potentially the outliers. Are these outliers? And, should we even consider them in the triangular distribution? And that's what this orange line does. So let's kind of connect this down to here. And we can see, I really like that new line I've drawn. You can see that blue triangle really reflects the nature of the data. And any issues we've got here, that's a small issue there. That's kind of net off by that issue there. So it's looking really, really good. So I think those are going to be the new parameters I'm going to suggest based on that triangle, the blue one. And that really reflects and matches up with the bulk of this data once we disregard these extreme outliers. Okay, let's go through. Let's now suggest our parameters. So remember, in a triangular distribution, we need an A value, which is the minimum. We need a B value, which is the maximum. And we need a C value, which is the mode. So let's go through and talk about the ones we've did. So A, I think, is unchanged, right? Because we're dealing with belly button fluff. 0 is the lower limit of the possibilities, so it makes total sense for 0 to stay, 0 milligrams to stay exactly as it is. The maximum, we redid this blue maximum line here to kind of roughly line up with the side or the actual shape of my distribution, and we kind of settled on 4.2 before all the gaps started. So let's do 4.2, or I've written GM before, but MG, 4.2 milligrams. In the mode, we roughly liked the mode, but we didn't quite like what they did because they picked 1, but the highest bar, as I said, was between 0.8 and 1. So I think the midpoint of that bar is probably a better, more appropriate use of a mode, and we're going to do 0.9 milligrams for that. So those are the new parameters that I'm going to suggest. I think if you did that well, you probably got the achieved or merit mark, but backing it up with justification, like we talked about, is how you're going to get the excellence mark. So let's add on 3 paragraphs, basically 1 for each of the 3 parameters, to then discuss and explain why we think that's the best possibility, or the best possible parameter for that. So let's start off with A. We'll just really go in order, I suppose. So the distributions parameters must not include any negative values, spelled negative wrong there, negative values as a person's belly button fluff cannot be negative. So that's what we were talking about before, how we justified 0 as our minimum. I can now link that to my actual value, A value, hence the A value or minimum should be 0 milligrams. So I like that. That's short and sharp. That one was a really easy one to justify. The next one is also going to be pretty easy to justify, the midpoint of 0.8 and 1 for B. So let's start talking about that. So the distributions parameters of the distribution's peak occurs between 0.8 and 1 milligrams. So the midpoint of this range of 0.9 milligrams would be an appropriate C value. I've written C value first. I was meant to do B, wasn't I? But appropriate C value slash mode for the new triangular distribution. And just adding words in like triangular distribution, c-value, putting in the units there, just so the marker clearly sees me connecting it to the context. So we've done the A value, we've explained the peak one quite well, I think, and now we've got the harder one to explain, the B value. And that was all about getting rid of the effect of the outliers and making sure the right-hand slope of the triangle reflected the distribution that we have. So let's start talking about why the maximum of 7.4, the original one, wasn't appropriate, and then transition that over to our new pick. So the original maximum of 7.4 milligrams may not be appropriate, as it does not follow the shape of the distribution, which has been dragged out by the potential outliers. Okay. Or outliers between, let's use some data, 4.4 and 7.4 milligram. So that was me talking about the outliers, and you see how that blue line, it's kind of dragged it out towards the orange line, and we can see that big void as a result. So I don't like that. So let's talk about the new maximum, which I've put down as 4.2. So a maximum of 4.2 milligram would be more appropriate, as the right hand side of the triangle connecting the peak and the x-axis would be a better fit for the distribution, well, for the data's distribution. So I really like that last one there. I think that's a really nice way to describe the right hand side of the triangle reflecting the actual data that we've been given. So hopefully that wraps up this question. Hopefully you can see it's a really, really accessible question. I think anyone probably could have thought about that and explained those. And even if you couldn't get all of them, you definitely could have done 2 or 3 of them. Okay, so we're now on to question number 36. And I've actually got a fairly unused part of the formula sheet here for you. And that's actually going to help us quite a bit with this question. Particularly this formula down the bottom here. I'll just kind of circle that already. So this question is going to all be about variance. It's all going to be about standard deviation, and this formula here, as I said, not commonly used in the exams, but it's going to be really relevant here. So let's break down the question. There's basically 2 variables as part of the formula. So we've been given the standard deviation of c plus t, and noting that's kind of what c and t mean are done here. So t relates to the number of towels used by a person on a given day. C related to the number of clothing changes they made during that day. And up here is the variation for T, also the distribution for T. We've been given some information from the previous question about the standard deviation of T and then the standard deviation of C. And using that formula down below that I mentioned, we're going to need to prove this. So are the events independent is only true if this formula holds up. So I guess the first thing to note, the relationship between variation and standard deviation is a different one, because this formula down the bottom is all about variation, this is all about standard deviations. So generally, or not generally speaking, but very explicitly, the variation of x is always equal to the standard deviation of event x squared. So that's the first thing we need to know. We can navigate and switch back and forth between the variation and standard deviation using square or square roots. And I guess the next thing to note is this messy formula down here, really, really importantly, this only works if the events are independent. So we can make a statement. So if T and C are independent, then so the variation of T plus C should be equal to the variation of event T plus the variation of event C. So we need to go ahead and calculate all 3 of these things. So we need to find the variance of T plus C, we need to find the variance of T, we need to find the variance of C. Once we've got all 3, we can check if the numbers match. If they match, we know they're independent. If they don't match, we know they are not independent. So let's start off by finding the variation of T plus C, because that one we can do off the bat with the number they've given us. So the number they've given us, the standard deviation of t plus c, is 1.754. So to find the variation of t and c, we just need to square that standard deviation. So we're going to go 1.754 squared, and that there is going to get this variation here, which is 3.0765, and that had a 4 dp rounding. As always, I'd always round to 4 decimals. So we can now figure out this variation of t, variation of c part here. And again, we've already got those numbers for the previous question, so what we're going to do is square those, right? So let's find, so the variation of t plus the variation of c. So that's going to be 1.405 squared. I'm then going to add on 0.5 squared. So that was the variation of t squared. So that's the variation of t, and then that's the variation of c. Now that I've got that, I can then plug it into my calculator, get my answer. So that there is going to be 2.2240, and that had a 4 dp rounding. So now that I've got that, so going back to my initial formula here, so if these events t and c are independent of each other, the variation of c, or variation of t plus c, should be equal to the variation of t plus the variation of c. And we can see these two numbers here are not equal to each other. So we can see that 3.0765 is not equal, I've written a 0, but that should be to 2.2240. So that means the variation of t plus c is not the same as the variation of t plus the variation of c. So we're writing that down, maybe down the very bottom here. So the variation of t plus c is not equal to the variation of t plus the variation of c. Gosh, very messy handwriting there. Apologies about that. Okay, I've done the math. I can now actually go ahead and answer the question. So this means that that t and c are not independent of each other. And that makes total sense because we're thinking of the number of towels used per day and the number of clothes changed per day. And for me, there's a correlation, or there's some kind of conditional thing happening between those, right? Because if you have a shower, you're probably going to change your clothes afterwards. If not, what's the point of having a shower? You're putting on your dirty clothes again. So that tells us there's a link between these two variables. So this tells us there is a link between, and I'm going to put in quote marks, I'm going to put in context, the number of towels used and quote marks the number of clothing changes. And then maybe I'll talk about the link. So that is the people who use more towels. So the people who use more towels will also use more clothes because they shower more. Also use more clothes because they shower more. Okay, so we're now on to question number 37, and this here does follow on to question number 38 as well, so we'll get to that shortly. So basically we've got a study of 138 people nationwide in 2011 about their belly button habits. So again, really weird theme to this exam, but we'll just have to go with it. And that was the distribution here, the number of times someone cleaned their belly button per week. We can see most people didn't clean it. So huge bar there. Most people cleaned it 7, so I don't think that's a coincidence, right? That's people who didn't clean it. That's people who cleaned it once a day. That's most people. They either cleaned it on a regular habit, i.e. once a day during their shower, or they didn't bother. And then you've got the people in the middle here who were just kind of I don't know, doing their own thing. I'm not quite sure what they didn't have a routine. They probably cleaned it, but not very reliably or consistently per routine. So we've got the data here, and they've suggested using a simulation of 1,000 simulations. They thought maybe a percent distribution was appropriate to model the number of times they clean their belly button. So from the data here, they found out that the mean was 2.8 washes per week during a 7-day week. And what they've done is they've done a model of a percent distribution to check out what the shape would actually look like. And they actually did that 1,000 times, and you kind of see the shape here. So you can see that there's the peak of this simulated data is around 2.8, and we can see there's a few people over here, and then again a few people down the beginning as well. So based on the simulation model and the original data observed, discuss whether a percent distribution model presented above appears to appropriately model the number of belly button washes per week in a 7-day week. Okay, so I've switched over to a text box to answer this question because it's all going to be wordy, and what I've done is I've typed up my thinking, how I'm going to approach these simulation questions, and they normally end up being the same. I normally ask myself, or I normally explain what exactly is the simulation in the question trying to do. After that, you then kind of consider the simulation itself, the appropriateness of it, maybe linking it to the context of the model that the question is trying to achieve. And then after that, you should clearly answer the question, how or what does the simulation suggest about whatever the question's getting at? And in this case, does the simulation suggest a percent distribution is appropriate? So those are the 3 paragraphs that we're trying to get at. So let's do paragraph number 1 first. What is the simulation here trying to do? And the simulation here, all it's really doing is it's comparing the distributed data of the number of washes in a 7-day week with the expected outcomes using our theoretical percent model. So that's kind of what we need to explain here. So the simulation compares the distribution of belly button washes per 7-day week with the outcomes under the theoretical percent distribution with a mean of 2.8 washes per week. Okay, so that wraps up the first question. So what is it really doing? It's comparing, I'm going to delete this paragraph started there, it's comparing the actual distribution with the theoretical simulated distribution. Outcomes under the perfect. Okay, so now they've got to do that, the second paragraph. So this here, it could go either way. So what I'm going to do here is I'm going to talk about, what I'm expecting to see. So if a percent distribution was appropriate, what should I be seeing? And then I need to compare the numbers of my graph to see, am I seeing that? So if a percent distribution was appropriate, these bars, I'll circle them with my computer pen. Hopefully it's going to work as I'm using the textbook. These bars here, the top of these bars, should all fit within, it's hard to see, within that grey band that I'm drawing there. So if they sit within the grey band, that means the percent distribution is correctly or roughly in line with the distributed data that we've got. If it's all over the show, like we've got here, that means it's not appropriate. So we can kind of see these huge gaps here, they're not within the grey band, and all of these aren't within the grey band. The only time it's kind of working is over here between 5 and 6, and I'd say barely working there as well. So let's talk about what we would expect to see, the peaks being within the grey cloud, and then let's talk about what we are seeing. Okay, so a percent distribution would be appropriate when the peaks of the actual distribution sit within the grey band slash grey clouds. This is what I like to call them. So that's when it would be appropriate. Let's now talk about what we're seeing if the simulation and the actual data backs that up. And in this case, it clearly does not. So however, this is not the case for our simulation and our distribution. So we've got that there, so let's now talk about it. So we can see that 0 and 7 belly button washes per week are significantly above the grey band or the grey cloud, and we can also see that the 1 to 4 range, kind of down there in the middle, that's also quite below the band as well. So either way, not good. So this graph here, terrible match. That simulation shows us something very clear that the theoretical percent model is not appropriate here. So let's talk about that before we wrap up with that conclusion. So we can see that 0 and 7 belly button washers are significantly above the grey band, and that 1 to 4 belly button washers are below the grey band. Okay, so that's what we've expected to see and what we're actually seeing. We can now wrap up with an overall conclusion. Do we think this is working, yes or no? And in this case, I think it's a clear no. So as the grey band significantly differs from the actual distribution of belly button washers, the simulation shows evidence that the proposed percent distribution may not be appropriate to model the number of belly button washers. And I'm amazing how well I did that last paragraph without the typing errors. Perfect. So that wraps up this question here. As I said, this is going to flow into question number 30. Flow into question number 38 as well. So let's get into that one there. So question number 38, propose and justify an alternative model that could be used for this. State the probability distribution and the parameters as part of your answer. Okay, so running through our list, so I guess the first question is what other distributions could there be? And we're only limited to the ones we've looked at, so just doing an abbreviation down the side here. So it could have been a percent distribution, could have been a binomial distribution, could be a normal distribution, could be a uniform or rectangular distribution, or it could be a triangular distribution. So basically there are options. So which we already know that a percent distribution is really bad. A binomial distribution, remember a binomial distribution is about having two outcomes. So that could be belly button wash or not belly button wash, not the number of belly button washes. So that's actually not going to work. And this here rules out the obvious ones because this is discrete data we're dealing with, because you can't have part of a belly button wash, right? You either wash it or you don't. So that means we're left with a continuous distribution options, which is a bit weird, and we may need to think of something called a continuity correction if your teacher chatted with you about that in class to do these as well. So looking at the shape here, we can see it's definitely not a bell curve, right? A normal distribution, it's not a bell curve, and normal distribution have an issue is we have a theoretical lower limit of 0 belly button washers, which doesn't quite work for that. So we can get rid of that. It's not going to be a normal distribution. So we're left these two here, uniform and triangular distribution, and I've drawn a rough kind of a rough uniform distribution shape here, and we can see it's actually not as bad as it looks, because it definitely doesn't look like a rectangle. But if we see here, you know, each gap, so obviously that's now a lot closer, that's a lot closer, that's a lot closer. So all of the bars are actually a lot closer. And if you think of a triangular distribution as well, drawing a triangle over that, we can kind of see the triangular distribution kind of follows the grey bands of a percent distribution, so that shape there doesn't work either. So based on that, there's no good answer to this one, I don't think. But I think a uniform distribution, potentially with a continuity correction to account for the discrete data, is probably going to be our best bet for this question. I've switched to the text, and then now the question basically says is, we need to suggest what model is appropriate and some parameters that might be appropriate as well. So that's kind of up here. So suggest an alternate model and the parameters that we need to have. So let's suggest a uniform distribution. So I suppose we should start talking about how we kind of got there. So on the face of the context, without seeing the actual distribution, one might be of the view that the belly button washing routines are random and could all be equally likely to occur. And I just want to pass on why I mentioned that. So basically, we kind of visually saw that a rectangular distribution is, it's looking the best out of a pretty bad bunch. But if you pretend you didn't see that graph, maybe you're of the view, maybe you're one of these people in the middle of the graph who kind of randomly wash their belly buttons, And it does make a lot of sense. Maybe belly button washing is random. So maybe we're going to see an assortment of 1 to 7s. And because we're expecting to see an assortment of it, so they might, they all might be equally likely to each other. And maybe because they're all equally likely, if you graph that, they're all going to have the same height as a bar, which, maybe is going to look like a rectangle. So that's what that's trying to sell is, maybe they're random, maybe they're all equally likely to occur, kind of like rolling a dice. So this suggests that a uniform distribution may be appropriate to model the number of belly button washes per 7-day week. So I've got that. So I've now stated the distribution that I'm going to use and why. So again, it's not because of the shape. It definitely doesn't look like a uniform distribution, does it? So if we were to use a uniform distribution, we're going to need to talk about the parameters. And the parameters really for a uniform distribution are A, which is a minimum, and B, which is the maximum. And the minimum is going to be easy to write in, right? So the minimum, like the question we did earlier on this video, the minimum is going to be 0 because you can't have negative belly button washes. You can have 0, which is the bulk of, so the mode of our data, and you can have anything more than that, but you can't have that. So the next one we want to talk about is we want to talk about what's the maximum going to be, and this is where maybe there's a bit of a debate. But for me, I think this 9 here is an outlier. So, for example, I think of my partner who's a nurse, and for me, I only have 1 shower a day in the morning because I'm a teacher. But she's a nurse, so she'll have a shower in the morning, like she always does. But after a shift, maybe she dealt with some gross stuff, like vomit or whatever during the day, she's probably going to come home and have another shower some of the days. And maybe that person there, that 9, maybe that reflects someone like that who's got a reason to have multiple showers per day. So I'm thinking that might be an outlier. So let's limit our data to the 0 to 7, which is basically the question is, how many times per day? So how many times per week do you wash your belly button? And it's, dealing with each day of the week. So let's go with 7 for that one there. And I'm going to write in brackets, I'm ignoring 9 as a potential outlier. So I'm just going to jot that there. Or spelling ignoring, I had a nightmare spelling that. Good typing in the other one, but not here. Okay, so let's now go into a bit more detail and discuss that in a bit more detail. So why would a uniform distribution, let's try to really sell it. So I'm going to first talk about the upper and the lower limits of my data. And here I've got clear ones, right? 7 because there's 7 days in the week, 0 because you don't wash your belly button. So I think that's a clear case for an upper and lower limit, which is one of the conditions of a uniform distribution. So let's start typing that. So a uniform distribution may be appropriate as there would be a clear lower and upper limit. Upper and lower limit. And while our distribution does not look uniform, so our distribution definitely does not, the distribution, or the true distribution, may be. So, for example, I just want to clarify that last point. So this is really just a sample, and we don't actually know what the real distribution is going to look like and the whole population. So maybe our sample's a bit weird. So we've got 138 citizens, part of a science project. For example, because it's a science one, if you were going to hospitals or if you're going to scientific research things, you might be dealing with chemicals, and because of that, you might, your distribution might be different. You might have to constantly wash your hands, part of the clinic, which means you don't feel the need to be as meticulous with your belly button washing or whatever might that be. So that's the first paragraph I want to talk about. So the next one I want to talk about is, they're probably going to be equally likely to occur. As I said, I can't really see a logical reason why one number of belly button washes is going to be more likely to occur than that. Obviously, excluding the data, but I don't know why. I feel like it would be a random assortment of people during the population. So the uniform distribution would require that each number of belly button washes is equally likely to occur. So I've got that one there, and then the next thing is, going to be the actual predictions that we make. So if we were using this percent distribution, we can see down the bottom there, we would have had a huge under prediction for 0. Like we would have been predicting very low, however the number's very high. The same would happen to 7 down here. Our prediction would have been very low, that it was 7. So by using a uniform distribution, whilst we're still going to be not having a great prediction, that unprediction isn't going to be as extreme. And the same in the middle, 1 to 4. We can see those 1 to 4 things, they are pretty far away from the grey cloud still, but the uniform distribution we have is likely going to drop the grey band lower, so that where that flat line is, and we can see those predictions 1 to 4 are actually going to be a little bit closer in a uniform distribution when compared with this percent distribution. So when looking at the percent distribution predictions, we are going to have a huge underestimate of people with 0 and 7 washes per week, and a overestimate of people with 1 to 4 washes per week. By using a uniform distribution, these prediction differences won't be as extreme. The under prediction of 0 and 7 washes per week will be closer, will be better, as will the over prediction of 1 to 4 washes per week. So not the best answer, I don't think, in the world, but I think the nature of this question, the uniform model, was not the best one here, so I'm really trying to sell a bad product here, to be honest. But I've done my best job. I've talked about the predictions will be better, but not great. I've talked about what a person might think if they didn't actually see their data, and I've maybe talked about the actual distribution, which we don't know. We just got a sample. The actual distribution may be very different to the distribution that we have here. So that wraps up all the excellence questions for this 2024 distributions exam. I hope you find them useful. I'm going to try put some time aside to make up some other videos on distributions. So keep an eye out on the Quick Maths website for other videos that pop up, and I'll put them up live when I make them.